So this video lesson is on the background of NMR spectroscopy and some of the details. There will be other clips later on, other lessons that go into various details or inspecting various spectra. So first of all, the electrons are not the only objects with spin. And again, spin does not necessarily mean that it is a little planetoid spinning on its axis, but what it does mean is that it interacts with a magnetic field. Protons and neutrons also have spin. Okay, so different elements that have spin. It works with this technique that we're going to be doing. NMR works with any nucleus that has a net spin, and that would be anything with an odd mass number. So if the nucleus has a certain number of protons, each of which has half integer spin a half, and each neutron also spin a half, they will be canceling out, netting out to zero, as long as that's an even number total, and it can't net out to zero if it's an odd number. So the useful ones are carbon-13 and hydrogen-1. Now hydrogen-1 is the normal isotope of hydrogen. That's just a proton nucleus and no neutrons. If you have deuterium, which is hydrogen with a neutron, then that does not have a net spin, and that will not be helpful for this type of spectra. The only thing it is good at is certain hydrogens are easy to swap out and swap back in, so it is possible to identify a specific signal going with that if you add some deuterium to the system. C13 is not the normal carbon. Normal carbon is carbon-12, which is a net spin of 0, but C13, about 1% of the carbons are C13, which means that it can be used somewhat. You get some different kinds of data from it. We'll talk about that in the next video clip. And so this is really about hydrogen, proton, NMR. So they're not equivalent when it comes into a magnetic field. That's the big deal. They are not equivalent. One of the states when the magnetic moment of the nucleus is aligned is more stable, lower energy, than when it is not aligned, when it's anti to the applied magnetic field. And that difference in energy depends on the strength of the magnetic field. Now, we don't need to know about all the mathy stuff here with the energy splittings, etc., but what we do need to know is that the gap here, the energy gap, does depend on the magnetic field. So if you have a really gigantic magnet, that gap will be bigger, and if you have a relatively small magnet, that gap will be smaller. And this is why when you go and have an MRI scan, which is a form of NMR, nuclear magnetic resonance, the magnets are gigantic because they're trying to get the best resolution they possibly can so they can see more details of what's going on. So big magnets for this technique. Now this particular energy gap is still going to be really tiny, no matter really how big the magnetic field is, and it's going to be in the radio frequency region of the electromagnetic spectrum. So radio frequency is very low energy electromagnetic radiation. It is lower than microwave, it is lower than infrared, it's lower than visible, certainly lower than any of the things that are higher than visible. If a photon of the appropriate energy is absorbed, then any nucleus that's in the spin plus 1/2, the lower state, can jump to the other one. Now, there are ones in both states at all times. They're not all in the lower state because they are so close that, given the amount of energy they have, some of them are in the upper state and some of them in the lower state. But it is entirely possible for this to absorb a photon and to jump. And we can detect that. We can scan for that. We can scan to see when are we putting in the right amount of energy to match, to be resonant with that energy gap. And we can do that in two different ways. Well, two different ways. we can have a big magnet that's just fixed and change the radio frequencies. So we would scan it, and when we got exactly the right energy, poof, we'd see a peak. And if we didn't have the right energy, we would not see a peak. It's also possible to just have one radio frequency and tweak the magnetic field. And so you'd have the energy, the radio frequency coming in, and as the magnetic field changed, poof, you'd have it so that it hits resonance. So it's really just that they have to match. And in MRI machines, they actually do something completely different. They can do pulse sequences. And so for any of you who've ever had one, you hear the clunk, clunk, clunk business going on. That's them doing these pulse sequences. And there are some fancy mathematical treatments that can unpack those spectra. We're not going to get into that mathematics. So this is what a spectrum looks like. The scale is given the symbol delta, and it is the chemical shift. Now we use deltas for a lot of different things. Usually we can tell which one we're doing at a given time. The units are parts per million, and this scale is normalized so that the numbers on here are going to be consistent no matter how big a magnetic field we're dealing with. These are going to be parts per million difference from the applied magnetic field in that. And how far are they off from a reference point? So when we have a really big magnet, we're still going to get the peaks at the same positions because of how we've defined the scale. But with a big magnet, we would get better resolution. So we would be able to zoom in closer and see more details, but we would still see the peaks at the same place. That's very helpful because we want to be able to compare data from different machines. So the zero for this scale is a specific compound. Where does its signal show up on this scale, and how different are other things from it? And the peak that's chosen is, this compound that's chosen is called tetramethylsilane. And it has 4 methyl groups around a silicon. So instead of it having like a carbon there, okay, it's a silicon, which is similar to carbon. It makes 4 bonds. But it has a lower electronegativity than carbon. It means it has less pull. And that is going to affect things. And almost every other thing we deal with that we might take a spectrum of has more pull than silicon. And it's going to show up on one part of the spectrum compared to silicon. In addition, TMS has 4 identical carbons, which means this can be used as a reference point in a carbon-13 NMR. You get a nice peak because they're 4 identical things. And it has 12 identical hydrogens, which means it's going to be a good reference for a hydrogen, a proton NMR. And there's no hydrogens on adjacent atoms. So this carbon here has got 3 hydrogens, but the silicon has no hydrogens. And that's actually a really important factor here. So the word vicinal comes from the same root as vicinity. And what that's going to mean is things that are on adjacent carbons. So if you have 2 carbons attached and they have a hydrogen each, then those 2 hydrogens are vicinal. We'll see that in a few minutes. So chemical shift, the units on this, most hydrogens, as I mentioned earlier, are going to fall, their spectrum is going to be further to the left, which is also called downfield, and it's a higher shift, more parts per million of a shift than the TMS. And again, that's because the silicon has such a low electronegativity. So the spin of electrons actually starts getting involved here too. It's not just about the spin of the nuclei, because the electron spin is actually going to be counteracting your applied magnetic field. So if you've got a lot of electrons around that nucleus, that hydrogen we're focusing on, then that nucleus isn't feeling the full external field. So it's going to show up in a different portion of the spectrum because it would take a different radio frequency to match that. The electrons are sort of canceling things out. But if you slurp the electrons away by something that's got a high electronegativity, then that doesn't happen so much. So when we take a look at the spectrum, I'll show you where you'd see various kinds of things. If the electrons are pulled away, we say that the nuclei are de-shielded. I'm sorry. So the different things. This is 0 ppm. This is the TMS. If we had some in this spectrum, we'd see a peak there. This is downfield over here. This is upfield over here. And the signals down here will be ones that are closer to electron withdrawing groups. Things that are uncovering, de-shielding those hydrogens. And there's 4 kinds of information we can get from this spectrum. So the first one is, how many peaks do you have? And this is the low resolution version, not trying to look at all the fine details. We have 3 peaks here. We have this one here, and this one here. And that means that there's 3 kinds of environments in this molecule. There are hydrogens in 3 different types of surroundings. And that's why they're showing up at different regions of the spectrum. So that's the first thing. Where the peaks are on the spectrum tells us something else. So we have a peak here. It's a little blobby, but it's a peak here at 3.8 in the ppm, one here at 3.6, and one over here at 1.0. Those 3, the shifts, the numbers that go with that, are going to tell us about those hydrogen atoms. This peak over here, they are close to this side of the spectrum. That means there aren't that many groups around them that are electron withdrawing. These are closer to something that is pulling electrons away. These are de-shielded. The area of the peaks tells us something also. So not only the type of environment, but how many hydrogens are in that environment. So right here, we've got this big peak, and these red lines here, the machines are actually measuring the areas under these curves. And they're showing it as a height. And for those of you in higher maths, that's an integration process. Other than that, we don't need to know how we get that information. So right here, if you look at this spectrum, there's a little height here and a little one here, and they're about the same size. And this one is quite a bit bigger. And if we took out a ruler, we would measure it. We would find that the ratio is pretty close to 1 to 1 to 6. And that implies a couple of things. It means that we have some multiple of 8 hydrogens in this molecule. Maybe we just have 8, 6 of them going into this peak, 1 of them for this peak and 1 of them for this peak. Or it's entirely possible we have 2 and 2 and 12. That would not be able to be distinguished here. So we've got 3 environments, but one of those environments has most of the hydrogens, and the other 2 environments don't have most of the hydrogens. So that's more information. Now, they also don't all look exactly the same. They have some fine structure. So this guy over here at 3.8 is a multiplet. It's a little blob with a lot of little peaklets. This one here, 3.6, this is a very high resolution scan, so it's mostly a singlet. There may be a slight secondary peak on there, and that's an artifact of the high resolution. We would discuss that on our next video. And this one over here is a doublet. So there's a peak here, and then there's another peak here. There's 2 peaks closely spaced together. And that's all extremely important information. That gives us information about the environment, but specifically, are there hydrogens next door? So you remember when I was mentioning TMS, tetramethylsilane, there are no hydrogens on the silicon directly, so there's no hydrogen next door to any other one. And that's really important. So let's take a look at that. So first of all, different chemical shifts go with different kinds of groups. And you have a data table for that, so you'll use that. I've got some reasonable ranges here. So this peak here at 1.0, this peak here is pretty indicative of hydrogens that are on a carbon that have no more than 1 carbon attached to them. There'd be a slight shifting if it was a CH2 group with then 2 carbons, 1 on either side. or a CH group with 3 carbons on the other sides. Carbon versus hydrogen is a slight difference. So this peak here is pretty indicative of a methyl group. There being 3 hydrogens on a carbon. Okay. Now this peak over here at 3.6, we're going to identify that, but it's really kind of hard to identify that because there's quite a wide range for what this could be. And what this is going to be is an OH group. It's going to be the H on an OH group. And the H on the OH group, again, that peak can be all over the place. Of course, I know what the spectrum is. But if you know how many atoms you have, you can start using that information better. And that's a singlet. And then this guy over here, this little multiple peak, the little raggy looking thing, is indicative of a hydrogen on a carbon, not on the oxygen, that one's on the oxygen, that is also attached to an oxygen. So the oxygen is going to affect the hydrogen. It's also going to affect the carbon, which is affecting the hydrogen. And so that's actually really important information. Because what this is telling us right here is that this peak here at 3.8 belongs to a hydrogen, which is attached to a carbon, which is attached to an oxygen. And if we were to find out that this molecule only has one oxygen, then we'd also know that there's another hydrogen on the other side of that, and we would have a group of 4 atoms in a row: hydrogen to carbon, carbon to oxygen, oxygen to hydrogen for an alcohol grouping. So that's important information. Okay, so combining some of this information, at 3.8 we have this 1H on a carbon, also on the oxygen, which I just said. 3.6, 1H on an O, which is an alcohol group. That's very specific. And this one is 6 hydrogens on carbons. But the carbons next door are not attached to any oxygens or nitrogens or anything weird. They're just attached to other carbons. And because it's 6 hydrogens, it's likely that it's going to be 2 methyl groups. Okay, so we'll see about how that unpacks a little bit later. Okay, so as I mentioned, there's this splitting thing. The hydrogens next door can affect things because these hydrogens have spins too. And so if you have a hydrogen next door and it's spin up, that's going to change the environment of the one we're caring about in a different way than if it weren't there at all, and in a different way than if it had a spin down. And so we're going to get 2 peaks, one of them for a hydrogen where the spin next door, if there's one hydrogen next door, if that spin happens to be up, then the hydrogen we care about is going to be experiencing that. And that's going to be different from some other molecule, which otherwise identical molecule, but where its next door hydrogen is spin down. And so that ends up being called a doublet. And I'm going to show you some examples of this in just a minute. In just a minute. If you have 2 next door, each one can be up or down. This is all independent. So you could have both of the ones next door being up. You could have both of the ones next door being down. And you can have one up and one down, or one down and one up. And those are 2 atoms. So there's 2 different ways that can happen. And these are 3 different environments. Now, this middle environment with one up and one down, that's just like there were no hydrogens next door. They're zeroing out. So the peak that goes here would be right where you'd expect it to be if there were no hydrogens. And there's 2 possibilities of ways that can be, and there's only one possible way for this one, which would be shifted because they're both up, and this one where they're shifted but they're both down. And this is going to lead to a triplet. So 2 hydrogens leading to a triplet, and the ratio of the areas are really very indicative. It's a 1 to 2 to 1 ratio. So 2 hydrogens gives us a 1 to 2 to 1 ratio. And we're going to see those kinds of spectra with a 1 to 2 to 1. And that means, hi, there's 2 hydrogens next door. Now this can go on. We can slice and dice this a lot, but this is going to be the last one I'm going to go through explicitly. If you have 3 hydrogens next door, and the reason that we care about this is because 3 hydrogens is a methyl group, and that's pretty common. And they can each be up or down, so you can have all of them up, all of them down. You can have 2 up and 1 down 3 different ways. You can have 2 down and 1 up 3 different ways. And so you get 4 slightly different environments. And the areas are going to be 1 to 3 to 3 to 1. And these ratios of areas, you may be noticing here, this is a Pascal's triangle relationship here. Assuming that all 3 hydrogens are identical, we would get this 1 to 3 to 3 to 1 ratio of the areas, and we'll call that a quartet when you have 4 little peaks. 3 hydrogens, 4 peaks. Okay, so here, if the peak, there's no hydrogens on this carbon over here, then it would show up right over there, smack where we'd expect it to be. But if there's this hydrogen next door, if this one is spin up, we're going to get one of these 2 peaks tweaked a little bit, and if it's spin down, we'll get the other one tweaked a little bit. Notice that they will be a little bit this way from the original and a little bit that way from the original, and the splitting is called J. So the splitting is how far they split from each other, and the original would have been symmetric in the middle. If there's 2 hydrogens, again, if one was up and one was down, it would be exactly where you'd expect it to be originally. Okay? And then 2 up or 2 down would push it twice as far out than this one, because there's 2 up or 2 down instead of just 1 up or 1 down, and vice versa. And if there's 3 hydrogens that are coupled in there, then none of them would be exactly netted out, and we would have the splittings looking like that. So in a very nice perfect spectrum, they would all look like nice, neat little singlets, doublets, triplets, or quartets. And so vicinal hydrogens, the hydrogens next door, the hydrogens in the vicinity. And let's take a look at our spectrum. This peak here is a doublet, and that means there is 1 hydrogen that is next to, that is vicinal, that is coupled to the hydrogens in this that are yielding this peak. This one here, okay, as I mentioned, is going to be that OH hydrogen, and it's not going to couple. And the reason for that is because the hydrogen on an oxygen can actually transfer out and in very easily. And this one here, it's like, what a little mess we have over there. A multiplet, not a quartet, a mess. And at a higher resolution, that little blobby thing actually has 7 peaks, if you zoomed in on it really, really closely. And the reason it has 7 peaks is because it's next to 6 things, 6 hydrogens. So this one would be next to 6 hydrogens. They could all be up. They could all be down. 5 of them could be up, and 1 of them could be down. You see how this could possibly work out? Yeah. Okay, good. Now, this 1 hydrogen peak is being split by 6 other hydrogens, 6 vicinal hydrogens. And this 6 hydrogen peak is split by 1 vicinal hydrogen. So what that's telling us is that these peaks are interacting with each other. The hydrogens that cause these 2 peaks are coupled to one another. The hydrogens that are making this peak are the same ones that are splitting, that are messing with that hydrogen's peak. And the hydrogen that's making this peak is splitting those. That's really important data. So here's what we've got so far. At 3.8, we have 1 hydrogen attached to a carbon. This one also has the O on it that we were talking about earlier, and it's next door to 6 more hydrogens. The peak at 3.6 is the alcohol group. The peak at 1.0 is 6 hydrogens on carbons, again, likely 2 methyl groups, and it's vicinal to the 1. These are next to each other. So how does that all work out? Well, this structure is consistent with it. And if we knew what its formula was to start this problem, and we knew that it was C3H8O, this is the only structure that is consistent with that. So let's take a quick peek at that. We have these 3 hydrogens and these 3 hydrogens, and they're equivalent. They are exactly the same. So they're all going to show up as 1 peak. these 3, and these 3. So 6 of the 8 hydrogens would be showing up as the one peak, which was at about 1.0 ppm. And it's a doublet because this hydrogen right here can be up, which would lead to one peak for these guys, or it could be down spin, which would lead to the other peak for these guys. Now, approximately half the molecules in your sample are going to have this B spin up, and approximately half the molecules are going to have this one B spin down. So the 2 peaks in the doublet are not exactly the same size, okay, but relatively similar in size. This one here, which is the peak at 3.8, this hydrogen, is being split by all of these, all of which can be up, all of which can be down, or any combination between. So the things that you can get from an NMR spectrum, particularly a hydrogen proton NMR, are the number of different kinds of hydrogens, environments that they're in, the general environment, based on where those peaks are, how many of each kind. So we had 3 kinds, but one of our kinds had 6 hydrogens involved with it. How many of each kind from the area, and what's next door. And the what's next door is actually really, really powerful because it lets us figure out what else is going on in the molecule. And that's it. And I'm going to ask you to please take a look at the other video I'm about to produce, which is going to be showing you some spectra along with models of the molecules right next door.